Stage is yours.
Thank you. Okay, so hello everyone. My name is Linda Blahova, and I'm thankful to the opportunity to be here and to present the research. So today I'm going to talk about blood smear leukocyte identification using an image segmentation approach. Well, the general problem that it's currently being observed. It's a manual biomedical image processing, mainly in laboratories where they have large data sets, from a microscope or similar products. And this is truly time consuming and can be very reliable on the human. It's okay. On the human error or at his I don't know, experience, let's say. This can result in inconsistent treatment path, or just inconsistent results from different researchers in the laboratory. To introduce the topic a little bit, we are going to talk about the microscopic images of blood smear. The dataset chosen for this research was a rabbit VPC dataset due to its large volume and variety of the images. I will talk about the dataset a little bit later on. Actually, the aim of the study is the identification of the region of interest, which is actually identification of leukocytes in the blood smear images. To set up some research goals, the main aim is actually to reduce the manual processing drawbacks, as I mentioned in the previous slides. What makes this study a little bit different from the other approaches which other universities are providing? It's the thing that the other researchers mainly do when they do some image segmentation. Often what they do, it's like they create their own data set, just like they have a data set of, I don't know, let's say 200 samples, but they just decide to use the 100 samples that are very similar to each other and very clear, they do not have any, I don't know, just scratches or just some bad things in the images, essentially. Actually, the aim of the study is to develop a system that doesn't require this. What I want to do is just, you take the all data set and you just run it through the system, and you don't have to selectively pick the good images, because I consider this a time-consuming thing. So this is what we want to exclude from the process. Okay, I said I would be talking about the dataset, so I already mentioned the dataset. It actually has around 40,000 sample images in total, but though these comes from two different microscopes. One was Zeiss, and I think the other one was Olympus or something like that. For the study, I decided to take 6 out of 7 albums from the Zeiss microscope, which is the 7 albums in total is around 2,500 images. But the 7th album had completely different graphical features. And since we're going to use the image segmentation, which essentially takes the graphical features, so it was kind of impossible to do it for all of them. So that's why only 6. The dataset was also chosen due to JSON annotations, and these would be used for the verification of the whole system, for the proposed process. On this image, we can see on the right side, it's a sample of an image from the dataset. The dark violet cells that we see there, it's the leukocytes. The other ones are the erythrocytes or red blood cells. And on the left side, we can see the annotation. So the cell is actually labeled by 2 experts, and they identified essentially the X and Y coordinates of the cell. So it would be used for the verification of the system. If the system decided correctly whether the leukocyte is in this position or not. The part of the research was also to explore some existing techniques because the aim is actually not to develop some new technique in image segmentation, but just to make use of the existing ones. So I examined some techniques as thresholding or contour extraction and similar. Since these techniques are available, so they are available in many software solutions or just libraries, so I decided to make use of this. And specifically, I chose ImageJ software because it has many implemented features that I can apply, and it's very user-friendly and easy to use. Essentially, you don't need to read the picture. It's actually just a sample of a macro. And by this, I just wanted to show that you can set up some pipeline of operations. So just like some set of operations applied to image. And it's a very short code, I would say, that you can just save and I don't know, maybe do some modification and apply to each and every image. So you don't have to do this repeatedly. You just have a bit of code and it works. About the operations or the pipeline that I mentioned, here are some main features that I used. I used histogram, RHB channels, some thresholding or dilation, and in the end, I analyzed the particles in order to get the region of interest or the leukocytes. And this depends on some parameters, for example, cell size or circularity and others. To automate this process, essentially, I decided to use a Java application, or I created a Java application in order, or actually what this application does is some preparation of the images. It essentially runs the whole process, to the ImageJ macro and stuff. Actually, at the end, it just loads the CSV files and they can be used for further processing or the evaluation, which is also part of the application. And the evaluation, as I mentioned, is based on the X and Y coordinates both from the system and from the experts as well. To make the user interaction easy, I decided to use a configuration file. This file is actually just a simple CSV file, and basically it includes all the necessary settings. So the user just interacts with one, file, and it's quite simple, I would say. It includes all the parametrical values for measurements and just like everything that user can change in the system. Two experiments were held to kind of make the solution running and to test it. So the first experiment was just taking one album of the Rabin VBC dataset, which was approximately, okay, I don't know why, but none of the images are showing in the presentation, or at least I don't see any. But that's okay. I can just talk about it. So there were actually graphs, to support the text. Essentially, on these 130 samples, the operations were applied, and I was evaluating the three aspects. There were correctly identified cells, then those that were not identified but labeled by experts, and the third category was the ones that were identified by the system but not labeled in the expert section. So essentially, as the correct ones, essentially to count the accuracy, I used the correct ones, and the ones that were identified by the system but not in the labels. But those had to be examined another way. like mostly manually, because it was just hard to implement in the system if the leukocytes are actually not in the labeled by the experts, because it would kind of like break the evaluation. Uh, the graphs would just really support this, but I'm doing my best. I don't know why they are not in the presentation. Okay, the other experiment, as I mentioned, was to just support the solution, and okay, I think that this, I think that the wrong presentation was uploaded, probably, but never mind. Basically, with the same configuration, it was just applied to a larger set of images, and the accuracy score that I got was essentially 91%, which was just 2% or 1% worse than in the smaller dataset. So I would say that the solution is pretty stable, and it kind of demonstrates the accuracy of the solution. That was the aim, actually, of the study, just to have a large sample, and you don't have to pick the images. So whether you take a small amount or a very large amount, it's just the accuracy doesn't change. About the results, just the results of the system essentially are some CSV files, which actually have the data about the position and some other things about the identified regions. Then some images. I don't know if it's. Oh, okay, you are able to see this. Some images that essentially have the region identified, and what's here, maybe you would ask why there in one cell there are two marked regions. So that is because the image segmentation just takes the graphical features, so just change the color. But in the evaluation, if these regions are within one cell, which can be compared to the things or the coordinates from the expert labeled cells. So essentially, if they were in similar coordinates, they were just evaluated as one cell. There were, I would say that there were a few exceptions with no cells, and or no cells, or just like a large amount of cells were identified. But this is the error, and this is just like the downside of the graphical feature evaluation, I would say. To conclude this, I would say that the contribution is to diagnose or just like to create a new data set because if the cells are identified, like the region is identified, the doctor or the laboratory worker can just mark the region of what type of cell is this. So they don't have to specifically search for the regions, but the system can actually find the region, and just they will just mark the cell. That would be all from my side. So thank you for the attention. Sorry for some disruptions with the presentation. It's really not my fault, but somehow I hope I managed to explain.
Questions? So today, one of the things that we saw in the class.
This one?
So yeah, because I'm not familiar with the classes. Like the game is to draw the outline of
Actually, the outline would be very hard to get because it's basically the same color as the red cells. So like it doesn't differ so much. So it would be actually really hard to get it by using just the graphical features. For that, probably you would just have to train some active learning or machine learning model or something. But using the graphical features, selecting the whole cell is not possible. So you will just select the nuclei. That's the best that you can do. And
how many employees this
well, because basically this region is what was marked in the labels from the extract. So this is just marked as Leukocyte. So when the system does the evaluation, then we just detect the color. So we detect the two, but it's actually one.
So this is a leukocyte.
Sorry?
This is a leukocyte. This one.
Yeah. So this is leukocyte. Yeah, with the dark nuclei. And these are just red blood cells.
So it detects, so this
Yeah.
one division marker X detects two.
Yeah, it
The other
takes
one
two.
one.
But then the evaluation algorithm works that way. That it just takes the region and it examines if the region is a subset of this bigger region. So if I don't know, there were like 3 or 5 and they were all a subset of the bigger region, they would be just evaluated as one. Okay. This right there. Oh. This one?
So these have been used by the district as determined or
well, essentially you have the image and you just do sequentially some of these operations and you are able to identify the regions on this whole image.
So these have been done on select or
in a pixel level, I would say, because you can also you can either mark those as squares and you can also mark the borders. You
and
know?
then how should the group together in the pattern because we saw.
What do you mean by group together?
If these are calculated at pixel level, and then we saw a contour, nice contour at the end.
It's essentially it also creates a CSV file, and which with both coordinates of the like x and y coordinate for every point. And from this, you either, as I said, you either have the whole border, like in one CSV file, so you just have the points, but it creates the whole border. So either you have this, or you just have the top left, the top left point, or you have the width and the height. So you can just calculate the width and the height.
Well, from the expert, or also from the humanitarian.
This is from IEEE. This feature that.
When you get where it's going to be expert,
Yeah, but essentially the aim was not to create the borders, but to create actually the process that is able to get the stuff. If you understand me, I mean this because this is the simple code for the operation. So essentially, in order to get from here to here, have to create a set of operations using the graphical features that will essentially somehow divide this from the background.
So the division is done by indentation.
No, the division, well, partly yes, partly no. The division is just, you know, at the end, it just gets to black and white. So this is the division that image they do. So when you see the white thing, it knows it's the cell. When you see the black, it's the rest. But to get there, it's the process diagram.
Then black and white.
Yeah.
This is a good case, maybe because 1, 2, 3, 4, 5 places of water big, but in most cases, you would speak as many white dots close together. There's not a big nice one.
Well, no, it's essentially it is a big nice one, and that is due to dilation. it's a feature or
So it's
a thing,
dilated and unite.
a thing that ImageJ offers, and I can just decide how many times do I want to repeat the dilation. It's also the process for image segmentation, and essentially it works like if you have two, or let's say, okay, I will come back here, and let's say you have this, right? This is very thin area. So in image segmentation, it can often happen that these things just separate, like here. But essentially, the dilate function does that it just takes the border and just like move, I don't know, 1 pixel further, like that. And this is basically what gives the opportunity to connect the pixels that are close to each other and have the white part.
What is it that decides to stop this dilating?
Well, that's up to the user.
Out.
You can, because essentially it just I don't know, move 1 pixel or just like a very very little amount, but you can do the operation. I don't know, you can do it once or you can do it 10 times. So that's
So you decide that at the beginning and then
Yeah.
let it go to
yeah.
data.
Exactly. Yeah. Okay. Any other questions?
Very short question. Thank you for your presentation. My question is, I'm not sure that my question is enough, correct? But what about data set coverage? I mean, what about capacity of data which you take into account to find a decision or problem or classification of the image? Your decision is based not on neural nets. That's a classical approach to classification.
Yeah.
But in any case, this problem is very simple.
Sure, but like what I wanted to demonstrate in the presentation or in the research itself is to take like a set of samples from a microscope. Like imagine you have a patient and you are examining his blood. So from one blood sample, essentially you get like 70 around 70 images of the blood. So essentially you will just need to examine these 70 images, but the solution was like created to or was just tested to a lot bigger sample of the images, so it shouldn't make a difference, if you had like the smaller set. So it should work.
This solution is creating information, new data sets, because from experts we need few markets in places, and this solution make it on all data sets.
And new artifacts, new
Yeah.
data set.
Yeah, and they will just label.
New data set of the blood cells with
Labels?
CSV labels in JSON or CSV file, which can use in amateur studies in this form.
In my opinion, it would be very nice to get any metrics.
They were actually there, but I don't know, the wrong presentation was uploaded. So none of the graphs and our architecture was there. So yeah, so probably just read the article.